Welcome back, everybody. Today we're talking about VORs. VOR stands for Very High Frequency Omnidirectional Range, and I'm teaching it with reference to Oxford Radio Navigation, chapter number 8. My name is Atif. Let's get started. Now, VOR is a navigation aid which was adopted by the ICAO in 1960 as a standard short range navigation aid. It produces bearing information with magnetic north at the VOR location. It is free from static interference and is usable at night, so it's technically a more advanced next generation navigation aid because our older one, the NDB, had a lot of problem with the static interference and the night problems. Now, our VORs work in VHF band from 108 to 117, but from 108 to 112, it is shared with ILS. Now, any number in this range, ignore it. Look at the first number after decimal. If this first number is odd, it's an ILS frequency. If it's even, it's a VOR frequency. As simple as that. So let me give you an example. 109er, decimal 65. Ignore this number and ignore everything else. The first number after decimal is even. Therefore, this is a VOR frequency. I hope you understand what I'm saying. Now, what are some of the uses of our big boy VOR? It's used as a beginning, end, and center line of your airways. It's used as a letdown for airfields that use published procedures, basically like VOR approaches and all that stuff. It's used as a holding point for aircraft and as a source of en route navigational position lines. Now, the emission of our VOR is known as Alpha Niner Whiskey. Alpha stands for main carrier amplitude modulated double sideband. So the main carrier wave is amplitude modulated and produces two sidebands on the top and at the bottom. That's what they mean by double sideband. Niner stands for composite system, and Whiskey, W, stands for the combination of telemetry and telegraphy. Moving forward, how does our VOR work? First of all, our VORs work by sending out two signals. The first one is called the reference signal and the second one is called the variable signal. Now, our aircraft has a receiver, the VOR receiver. It measures the phase difference between two signals from the transmitter. And also a very important point to note that in the normal VOR, the 30 Hz frequency modulated wave is our reference wave and the 30 Hz amplitude modulated is our variable. Okay? I hope I'm clear? Okay. Now, the VOR navigation equipment in the aircraft's cockpit calculates the difference between the reference and the variable phase to determine the radial on which our aircraft is on with respect to the VOR. So let's say your aircraft was here. So you got signals. The black one is your reference and the red one is your variable. And the difference came out to be 0, 9, or 0. So that's how they measure the phase difference. Now, before we move any further, I want to make something very clear. Radial simply means your QDR. What is QDR? QDR is magnetic bearing from a station. What's the opposite of QDR? The opposite of QDR is QDM, magnetic bearing to the station. Okay? Now, how do we identify VORs? We know how they work, we know what it gives us, we know what this blah blah reference and variable is. How do we know that we're using a VOR? Like in our NDBs, we had Morse codes and identifiers. Similarly, we have 3-letter codes. Example, Delta Papa November, DPN. This is a Delhi VOR. You can also hear 3-letter Morse codes. Now, our VORs. Okay, do you guys remember a very big problem about NDBs? If the NDB station was not working, there is no way for the pilot to know. But in VORs, if the station goes off, now when does the station go off first? if the signal strength reduces by 15% or more, there's loss of power by 15% or more. Secondly, if the monitor fails, or if the VOR is giving errors in reading, like you're at 09 or 0, is giving you 09 or 2. Like it's that accurate. Bearing error of more than 1 degree means the VOR is unusable. Also, your aircraft system, like in the cockpit, the display, a display comes saying off. A display like off is going to appear in the cockpit, which tells you that the VOR is no longer operational. This is what the polar diagram of a VOR is. It's called as a limaçon, or some people call it limacon, whatever you like it. Moving on, types of VOR. The conventional VOR, about which we discussed, which has a 30 hertz, what type of wave? Frequency modulated reference, and 30 hertz amplitude modulated variable. Perfect. Now, what is a BVOR? BVOR stands for broadcast VOR. It gives weather info, airfield info, and yeah, that's pretty much it. It just broadcasts information. Now we have something known as the Doppler VOR. We'll get into it later, but this is better than conventional. This overcomes sight error, which is an error of conventional. We'll get into that in a bit. Now, TVOR stands for terminal. These are low power VORs. That's it. Nothing much, and they're only available at major airfields. Like, you're not gonna find it in a small unpopular airport, you know. Now we have something known as a VOT. This stands for a test VOR. It's used only for testing. It's not used for navigation or anything. It's strictly only used for testing. Now, VORTAC is a combination of VOR and DME. Okay? So what is a VORTAC? A VORTAC is a co-located VOR and a DME. That's pretty much it. Moving forward, some things which affect the range of our VOR. The theoretical range formula is same as the NDB. 1.23 times the square root of the height of receiver plus the square root of the height of transmitter. Now, HR means height of receiver, which is your aircraft, and HT means the height of the transmitter, which is your VOR. Now, other things that affect is the power. Higher the range, and certain things like uneven terrain, high ground, mountains, man-made structures like buildings. What these do is that these cause the VOR bearings to be stopped, reflected, or bent. So what happens is you have your VOR here. My apologies, that's not how you draw VOR. VOR is like a pentagon. Okay, this is your VOR, and let's say there's a mountain here, and let's say this is your aircraft. Okay, so instead of sending signals directly to your aircraft, it's going to bounce from the mountain here, there, and then go to your aircraft. So it's going to give your aircraft wrong bearing information. I hope I'm correct. I mean, I don't hope I'm correct. I hope you understand what I said. Moving on. Now, wherever these errors will exist, like if the VOR is not located in open ground, they're going to tell you. The AIPs of your country is going to have them published. For example, errors up to 6 degrees may be experienced in sector 180 to 195 degrees. It's going to be mentioned in the AIPs, wherever there's VOR, which are going to cause some errors. Moving on to a very important topic, designated operational coverage. Now, what this does is that it's a specific amount of coverage which guarantees, I don't know if the spelling's correct, man, just forgive me for that one. It guarantees no co-frequency interference. What it means is, like, in NDBs, let's say you have like 2 NDBs, there's going to be some problem if your aircraft's like flying here. It's going to get signals from both the NDBs, and it's going to have problems. But in a VOR, we have something called as a designated operational coverage. What this does is that it tells you that in certain range or radius, you're not gonna have any problem. Like, let's say, let me tell you how it's gonna be published. Okay, let me tell you how it's published. Let's say they give like DOC 10 0 by, let's just say 35. What this means is that no problem using this VOR up to 100 nautical miles and 35,000 feet. So what it's saying is that there's gonna be no problem that the aircraft is gonna face up to 100 nautical miles from the VOR and up to 35,000 feet. So a DOC guarantees no interference and no problems in the information that you get from a VOR. Now, if you use a VOR outside the DOC, the designated operational coverage, you could get a lot of navigational errors. Okay, could be anything, maybe a small error of 2 or 3 degrees, or even massively huge errors. Now, we're talking a lot about errors, so let's talk about them a bit more. Now, sight error. What is this thing? Sight error is caused by uneven terrain. Not even, like uneven terrain. Now, where does this happen? It happens at the VOR. Sight error. It happens at the VOR site. Okay? The error is going to be about plus or minus 1 degrees. Next, we have propagation error. What happened is like, let me tell you. First of all, this is also like plus minus 1 degrees total. And there's going to be a lot of problems by terrain, buildings. That's pretty much it. Basically your waves after leaving the site gets reflected or bent, and scalloping also occurs over here. So propagation error is like, let's say this is your VOR, this is your aircraft. There's a lot of mountains, there's a lot of buildings. So there's going to be a lot of bending and reflecting. And all this is going to cause errors in the propagation path of the VOR. Now, these bending from buildings and terrains causes the CDI to slowly, rapidly shift from site to site. And sorry for the confusion, VOR scalloping is basically something which is defined as an imperfection or deviation in the received VOR signal. Okay, I apologize for that. Moving forward, airborne equipment error. Obviously, you can't manufacture something perfect. There's gonna be an error in the aircraft. This is up to plus minus 3 degrees acceptable. Now, if you add all of them, the aggregate error should not be more than 5 degrees. Now, this 5 degrees is a very interesting number. Do you know why? Because your airways, they're what? 10 nautical miles wide, if you have learned in regulations, right? And if you have 2 VORs, let's say 200 nautical miles apart, and you use the 1 in 60 rule, try to figure out yourself why is the aggregate error of 5 degrees. Use the 1 in 60 rule, take 2 VORs, place them at the maximum allowed distance that they can be placed, which is 200 nautical miles, and try to figure out why did they use this 5 degrees, okay? Let me know in the comments if you have watched till here and if you find the answer to that. Cone of ambiguity, or the cone of confusion. Okay, ladies and gentlemen, this is your VOR. So your VOR is sending signals, right? There's going to be a point when your aircraft is overhead the VOR. When your aircraft is overhead the VOR, there's going to be a lot of problems. An off flag is going to come. The to and from are going to interchange very rapidly and fast. And it's just going to be a very confusing thing for your aircraft. Okay? Now, where does it happen? Nowadays, it's generally 60 to 80 degrees above the horizon. Like if you're flying in this range, you're gonna get all this problem and your needle is gonna go crazy. It's gonna go crazy. Okay. Now, Doppler VOR. I'm sorry I didn't explain you there, but let me tell you the thing about Doppler. Now, Doppler is a second gen VOR. Okay, it has more accurate bearing, and it's less sensitive to sight errors. Now, the transmission difference, there's only one difference. Here, the reference signal is amplitude modulated and the variable signal is frequency modulated. Now, because of this frequency modulation in the variable signal, it overcomes sight errors and gives more accurate readings. Moving on to the last part, airborne equipments for VOR. Now we know what should be there on the ground, should be, placed in an open field to prevent it from certain errors. Now let's see, what do we need as pilots inside our aircraft? We need three things mainly. To name them, number one is an aerial, something to receive it, right? For slower aircrafts, aerial is fitted on the fuselage, but for faster aircraft, it's a blade type fitted on the vertical fin on either the left or right of the fin. Now we also need a receiver, which is there in the avionics bay of your aircraft. And finally, an indicator in the cockpit as a gauge for displaying the information. Now the information is displayed on RMI. Yes, RMI is used for NDBs and VORs both. On a CDI, a course deviation indicator, or an HSI, horizontal situation indicator. Okay, thank you guys. We'll continue with displays, interpretation, and questions related to NDBs in the next part.